Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So today we are going to talk on the module Landauer and Büttiker Formalism for Conduction in Confined Structures from the paper Nanoscience and Nanotechnology first. So after completing this module, the students will be able to first, Landauer-Büttiker formalism will be discussed in detail. Second, the Landauer formula for coherent transport with many channels, two leads with many channels or subbands, and many leads with many channels or subbands will be discussed. Lastly, we will also discuss about the applications of Landauer-Büttiker formula. So students, let us start with a basic introduction about the module. The Landauer-Büttiker approach treats transport as a transmission problem for electrons at the Fermi level. The ohmic contacts are modeled as current injecting and collecting reservoirs, wherein all the inelastic scattering is assumed to be taking place exclusively. So the zero field conductance quantization of an ideal 1D conductor and the smooth transition to the quantum Hall effect on applying a magnetic field are seen to follow directly from the fact that a reservoir in equilibrium injects a current which is shared equally by all the propagating modes. Another important assumption is that the system is connected to reservoirs by ideal quantum wires which behave as waveguides for the electron waves. Landauer-Büttiker formalism. The Landauer formula, named after Rolf Landauer, is a relation between the electrical resistance of a quantum conductor and its scattering properties. Conduction in a macroscopic conductor is given by the Ohm's law, that is, G equal to sigma A by L. Here A is the cross-section area of a conductor of length L having the conductivity of sigma. So from this relation, G tends to 0 as A tends to 0, implying that the conductance vanishes as the conductor becomes narrower. Also, G tends to infinity for very small conductors as L tends to 0. Such behavior is based on the simple assumption that the conductivity of a conductor does not rely on its dimensions, since it is the macroscopically described quantity and is imagined to be uniform over the length of the conductor. As the dimensions of the conductor approach the atomic scales, this uniformity in the conductivity is disturbed and Ohm's law ceases to apply. This failure in Ohm's law has been observed in experiments on quantum point contacts and the atomic sized wires, wherein a staircase type of behavior has been seen in conductance during the narrowing of point contact and the elongation of wire respectively. One significant challenge is defining the characteristic length or the dimensions of the conductor at which macroscopic explanation fails. The significant length scales deciding this dimension are de Broglie wavelength associated with the kinetic energy of electrons. Second is the mean free path or average distance traveled by the electron before altering the momentum. For example, scattering with impurities leads to the change in momentum. And lastly, the phase relaxation length or average distance traveled by the electron before destroying its phase. So the phase loss occurs because of inelastic scattering attributable to electron-electron and electron-phonon interactions as shown in this figure. So here Lm denotes the ballistic transport limit and L phi denotes the coherent transport limit. Now a conductor demonstrates the ohmic behavior when its size or dimension is sufficiently bigger than these lengths. This characteristic length depends on the type of material and gets affected by magnetic field or temperature. If the dimensions of given conductor are in between the microscopic and macroscopic, it is termed as mesoscopic conductor with a dimension of few nanometers. Microscopic conductors are of nanometer size and are often termed as atomic sized conductors as shown in this figure. So this figure schematically represents the atomic wire. An electron coming in from the left head is partially transmitted through the wire to the right head. Electron transport is described by quantum mechanical transmission probability amplitudes TNM, which can be calculated at the Fermi level if the applied voltage V is small. The conductance of the wire G equal to di by dV can be expressed in terms of the normalized transmission probability amplitudes TNM by the Landauer-Büttiker formula. The Landauer-Büttiker approach is based on the quantum mechanical scattering technique to calculate the electrical conductance in very small devices. For an elementary description of quantum conduction effects, 1D mesoscopic semiconductor structure such as quantum wires are ideal candidates. If the length of the wire is less than the electronic mean free path, there is no scattering and the transport is ballistic. So let us assume that the 1D quantum wire is connected by ideal leads which do not cause any scattering, to the reservoirs having Fermi level EF1 and EF2. Suppose a voltage V is applied across the leads. Therefore, the potential energy between the two levels, that is EV, will be equal to EF1 minus EF2. Noticeably, at low bias voltages, only the electrons near the Fermi energy contribute to the current in linear response region. So the bias voltage is assumed to be equal to the difference between the chemical potentials of the left and the right electrodes. So the current across the wire should be given by the product of the concentration of electrons from the density of states in energy difference EV, the electron velocity VE, and the unit electron charge as I equal to E multiplied by N1D as a function of E multiplied by V as a function of E multiplied by EV, where N1D will be equal to 2 by N multiply the NHVG. So for electron moving in one direction, current can be written as I equal to 2E square by H cut multiplied by V, which is interestingly independent of the carrier velocity. So the value of conductance, that is G, which is equal to I by V, becomes G equal to 2E square by H cut. Now a conductor demonstrates the ohmic behavior when its size or dimension is sufficiently bigger than these lengths. This characteristic length depends on the type of material and gets affected by magnetic field or temperature. If the dimensions of given conductor are in between the microscopic and macroscopic, it is termed as mesoscopic conductor with a dimension of few nanometers. Microscopic conductors are of nanometer size and are often termed as atomic sized conductors as shown in this figure. So this figure schematically represents the atomic wire. An electron coming in from the left head is partially transmitted through the wire to the right head. Electron transport is described by quantum mechanical transmission probability amplitudes TNM, which can be calculated at the Fermi level if the applied voltage V is small. The conductance of the wire G equal to dI by dV can be expressed in terms of the normalized transmission probability amplitudes TNM by the Landauer-Büttiker formula. Let us now discuss the Landauer formula for coherent transport with many channels. Let us first discuss the two leads with many channels or subbands. So this figure shows a system with extensions beyond one dimension. There are two leads with scattering center positioned between them, with each lead having several subbands arising from transverse states. These subbands are also called as the modes or the channel. So this figure elaborates the coherent transport through a system with two leads, each with multiple propagating states. It is interesting that the transverse potential of each lead remains constant along its length. So, this is a part of the definition of a perfect lead. And any regions with variable potential must be considered as a part of the scattering center. So, the wave function within the lead can be written as psi r equal to summation over n Vn to the power minus half multiplied by an exponential iota knz plus bn exponential minus knz multiplied by unr. So transfer states are labeled by n with wave functions unr and energies epsilon n. So the total energy E is equal to epsilon n plus h cut square kn square by 2m. So states propagate if E is greater than epsilon n and it decays otherwise. The factor with the velocity Vn of each mode normalizes the states by flux rather than the density. So generally, the two leads are not identical. So the energies of the 1D subbands and so are the number of propagating states in each n left and n right. So psi a psi z, which is written as a exponential iota k1z plus b exponential minus k2z for z less than 0, and it is equal to c exponential iota k1z plus d exponential minus iota k2z for z greater than 0. Injecting a wave from the left purely in mode M, the scattering center misses the different modes, so the scattered wave has contributions from all outgoing modes on both the sides. The wave functions in the left and the right leads becomes psi left r equal to v lm to the power minus half u lm exponential iota klmz plus summation over n equal to 1 to infinity vln to the power minus half rnm ulm exponential minus iota kln z. So psi right, which is given by summation over n equal to 1 to infinity vln to the power minus half tnm unr exponential minus knr z. So the matrix T can be constructed from the coefficients T and M in the above equation, giving the transmission magnitude for an electron incident from the left in the mode M to be transmitted on the right in the node N. So we restrict T to propagating states giving dimensions of n right multiplied by n left. So one reason of using T is that it contains sufficient information to find the conductance. Suppose electrons are injected in the mode M. The electrons emerging in mode N contribute 2e square by h multiplied by the modulus of Tnm the whole square to the conductance. So the velocity of different modes is taken into account by the normalization and does not clutter this result. So the total conductance is obtained by summing over all the input and the output modes, that is G equal to 2E square by H multiplied by summation over Nm of modulus Tnm the whole square. So the relation describes the conductance G equal to di by dV as a sum over the normalized transmission probability amplitudes Tnm between all right-going modes N and M in the left and the right leads respectively. So the factor of 2 in this relation is due to the electron spin degeneracy. When the conductor is connected with semi-infinite ideal crystalline leads, the modes can be expressed as block functions. So these are the plane waves commonly used to model the metallic electrodes. The conductance can be written in more compact form by using the Hermitian conjugate matrix of T, which is defined by T dagger Mn equal to Tnm star. Then G equal to 2E square by H multiplied by summation over Mn Tnm multiplied by Tnm star equal to 2E square by H multiplied by summation over Mn Tnm T dagger Mn equal to 2E square by H multiplied by summation over N of T dagger Nn, which is equal to 2E square by H multiplied by trace of T dagger equal to 2E square by H multiplied by trace of T dagger T. So this is usually quoted result where Tr is the trace of the matrix, the sum of its diagonal elements. Also the product T dagger is a square, although neither T or nor T dagger need be, and that the two expressions for the trace are equal even when T dagger and T dagger T may not be of the same size. The Landauer-Büttiker formalism takes into consideration a single particle picture of the electronic transport. In other words, it assumes the electrons as non-interacting entities. However, the electron-electron interactions can be partially considered in a mean field approach where the transmission amplitudes can be determined from the single particle equation as minus h cut square by 2m del square plus V effective R minus EF this whole multiplied by psi R equal to 0. Here the effective potential V effective accounts for the interactions of an electron with the average field of other electrons and nuclei. Let us now discuss the other case, that is many leads with many channels or subbands. So this figure shows us the geometry of a sample for coherent transport with many leads. So first shows the specific example, and BCD figure shows a D-junction, 4-terminal measurement of longitudinal resistance, and the D1 shows a microscopic Hall bar. Let us now consider a particular lead and a mode M alpha. So we are interested only in the deviations from equilibrium. So the excess current that impinges on the sample from this lead is I m alpha incident equal to minus 2e by h delta mu m. The change in the Fermi energy delta mu m equal to minus EVM, where Vm is the applied voltage. So Im alpha incident will be equal to 2e square by HVm, which is the same for all Nm modes in this lead. So the total current in the lead N due to the electrons injected from a different lead M is given by summing over all the modes in the two leads, and it is given by INM equal to minus 2e square by h Vm multiplied by summation over beta equal to 1 to Nn, summation over alpha equal to 1 to Nm of Tn beta m alpha modulus square. All expressions for current involves the similar sums over the modes in both the leads. So it is similar to the trace with the additional subscripts on transmission coefficients to label the leads. The transmission and reflection coefficients which absorb these traces are given by Tnm is summation over beta equal to 1 to Nn, summation over alpha equal to 1 to Nm, modulus Tn beta m alpha this whole square. And similarly, Rm will be by replacing T by R. So the net current injected into the lead M is given by the incident current minus the reflected current. That is, the net current will be IMM equal to 2e square by h multiplied by Nm minus Rm multiplied by Vm. So the conservation of current requires that this be equal to the total current injected from lead M that leaves the sample, though other leads, that is IMM equal to summation over n and not equal to m INM. So this leads to a sum rule on the transmission coefficients, that is Rm plus summation over n and not equal to m Tnm equal to Nm, which is a simple generalization of R plus T. We have now calculated the currents due to electrons injected from lead M. So now the summation of all leads contributions is required. Lead N causes the current minus 2e square by h cut multiplied by Tmn multiplied by Vn in lead M. So the total current in lead M is Im equal to 2e square by h cut multiplied by Nm minus Rm multiplied by Vm minus summation over n comma n not equal to m Tmn Vn. This is the Landauer-Büttiker formula for the conductance of a system with many leads. So it can also be written in terms of the square of the conductance matrix, whose dimension is given by the number of leads, that is In equal to summation over n Gmn Vn, Gmn equal to 2e square by h cut multiplied by Nm minus Rm multiplied by delta Mn minus Tmn, this square bracket close. Let us now discuss the applications of Landauer-Büttiker formula. First is the quantum point contact for a 2-degree electronic transport in single molecule junctions, longitudinal electronic transport in carbon nanotubes and 2D graphene, electronic transport in nanoparticles and chains of nanoparticles, And last one is multi-terminal quantum point contacts. So students, let us now summarize what we have learned in this module. Firstly, the Landauer-Büttiker formalism was discussed in detail. Secondly, the Landauer formula, which is used to or the study the coherent transport with many channels. For example, two leads with many channels or subbands and many leads with many channels or subbands. They were discussed in detail in this module. Lastly, the application of Landauer-Büttiker formula was also discussed. Thank you.